Section 1 Introduction. The introduction of this paper delves into the exciting world of text-to-image diffusion models, such as DALL-E 2, Imagine, and Stable Diffusion. These models are impressive, as they can generate a wide range of high-quality images simply by using natural language instructions. Their power has given rise to a myriad of image editing methods, like fine-tuning models for specific object generation, translating images, inpainting images, and editing objects. All of these applications have made it much easier for users to create and modify images through the use of natural language, greatly boosting efficiency. As video content becomes more popular on social platforms, the demand for improved video creation tools has increased. However, using image diffusion models directly for videos presents a significant challenge: severe flickering issues. To solve this, researchers have recently shifted their focus to text-to-video diffusion models and have proposed 3 potential solutions. The first solution involves training a video model on a large amount of video data, which consumes a considerable amount of computing resources and creates compatibility issues with existing image models. The second solution recommends fine-tuning image models on a single video, but this approach can be inefficient for lengthy videos and might even lead to degraded performance due to overfitting. The third and final solution focuses on zero-shot methods that don't require any training and instead impose cross-frame constraints during the diffusion sampling process for temporal consistency. This approach needs fewer computing resources and is mostly compatible with existing image models, showing potential promise. However, a limitation of current cross-frame constraints is that they're restricted to global styles, meaning they don't preserve low-level consistency. As a result, while the overall style might be consistent, local structures and textures may still flicker. To apply image diffusion models successfully to videos, we need to ensure temporal consistency, zero-shot capabilities, no training or fine-tuning required, and flexibility to be compatible with off-the-shelf image models for customized generation. Recognizing these challenges, this paper introduces a new strategy using the zero-shot approach for model compatibility and focusing on maintaining low-level temporal consistency. We propose a novel hierarchical cross-frame constraints for pre-trained image models, using optical flow to apply dense cross-frame constraints to produce coherent video frames. We use the previous frame as a low-level reference for the current frame, and the first frame acts as an anchor to regulate the rendering process, ensuring there are no deviations from the initial appearance. In addition to global style consistency, our method also ensures consistency in shapes, textures, and colors at the early, middle, and late stages of diffusion sampling. This lightweight yet innovative modification achieves both global and local temporal consistency. Furthermore, we present a novel zero-shot framework for text-guided video-to-video translation, comprised of 2 parts: key frame translation and full video translation. The first part uses pre-trained image diffusion models with hierarchical cross-frame constraints to generate key frames. The second part propagates these key frames to other frames using a method involving temporal-aware patch matching and frame blending. Though diffusion-based generation excels at content creation, it can be inefficient due to its multi-step sampling process. On the contrary, patch-based propagation can efficiently infer pixel-level coherent frames but struggles with creating new content. By combining these 2 components, our framework strikes a balance between quality and efficiency. In summary, the main contributions of this paper are as follows. 1. We introduce a novel zero-shot framework for text-guided video-to-video translation that achieves both global and local temporal consistency, requires no training, and is compatible with pre-trained image diffusion models. 2. We propose hierarchical cross-frame consistency constraints to enforce temporal consistency in shapes, textures, and colors, which adapt image diffusion models to videos. 3. We blend diffusion-based generation and patch-based propagation to strike the perfect balance between quality and efficiency. Section summary. Recent text-to-image diffusion models have led to the emergence of image editing methods, but applying these models to videos leads to flickering issues. Researchers have proposed 3 solutions, with the zero-shot strategy showing promising potential. However, current cross-frame constraints are limited to global styles and cannot preserve low-level consistency. This paper introduces a novel zero-shot framework for text-guided video-to-video translation, which achieves both global and local temporal consistency. Requires no training, and is compatible with pre-trained image diffusion models. The framework combines hierarchical cross-frame consistency constraints and hybrid diffusion-based generation and patch-based propagation to strike a balance between quality and efficiency. Section 2 Related work. The research area of text-driven image generation has attracted substantial attention. This concept involves creating images based on descriptive phrases, which is an intuitive and flexible approach. Earlier methodologies leveraged generative adversarial networks, GANs, to produce lifelike images. Further advancements saw the introduction of autoregressive models, which use the transformer architecture's rich expressivity to model each pixel in an image as part of a sequence, with a dependency relationship between every pixel. Notable examples of this approach are DAL-E and CogView, both of which train an autoregressive transformer on tokens from images and texts. Make a Scene adds an additional layer of complexity by considering segmentation masks as a condition. Recent research has shifted focus to diffusion models for text-to-image generation. In these models, images are created through a step-by-step noise removal process. DALL-E 2 and Imagine have made strides in this area by introducing pre-trained large language models as text encoders. This helps to better align the image with the text, and cascade diffusion models are then used to generate high-resolution images. Glide further enhances this process by offering classifier-free guidance for text conditioning. Latent diffusion models take a different approach, applying noise removal in the low-resolution latent space of VQ-GAN to enhance efficiency. For more detailed information on this topic, we refer to an extensive survey available in our reference list. Beyond general image diffusion models, researchers have also explored custom models. For instance, Textual Inversion and Dream Booth use specialized tokens to capture novel concepts and generate associated images from a limited set of example images. Another innovation, LoRa, speeds up the fine-tuning of large models by learning low-rank weight matrices that can be added to existing weights. ControlNet fine-tunes a new control path that allows for pixel-level conditions like edge maps and poses, which enable the production of detailed images. The method we propose does not modify the pre-trained model and can be used alongside these existing techniques. This allows us to take advantage of Dream Booth and LoRa to improve customized video translation and use ControlNet to guide the creation of time-consistent structures as depicted in the figure in our research paper. Section Summary. Previous works on text-driven image generation have explored the use of GAN and autoregressive models, such as DAL-E and CogView, to synthesize realistic images. Recent studies have focused on diffusion models for text-to-image generation, while customized models like Textual Inversion and ControlNet have been developed to generate images with specific conditions. The author's method is orthogonal to these existing techniques and can leverage them for better customized video translation and temporal consistent structure guidance. Section 2.2 Video Editing with Diffusion Models. We will discuss the use of diffusion models in video editing, specifically for creating videos from text inputs. Previously, the video diffusion model has been employed, where a 2D U-net used in image models was extended to a factorized spacetime U-net for video applications. Models like Imagine Video scaled up the video diffusion model by using a series of spatial and temporal video super-resolution models. Another technique, the Make a Video model, utilized video data in an unsupervised way to teach the movement that drives the image model. While these methods are promising, they are heavily reliant on vast video data for training. Another model, Tune a Video, inflates an image diffusion model into a video model with attention across frames and refines it on a single video to generate videos with associated movements. Edit a Video, Video P2P, and Vid2 Vid0 models also make use of null text inversion, a technique for exact inversion that keeps the unedited regions intact. The downside of these models is the need for refining the pre-trained model or optimizing the input video, which can be time-consuming. Recently, zero-shot methods have emerged, offering an advantage as they operate without a training phase. These methods are naturally compatible with pre-trained diffusion variants like Instruct Pix2Pix or ControlNet and can accommodate more flexible conditions such as depth and edges. For the editing process, the editing masks are identified by prompt2prompt, which shows the channel and spatial region to keep. An approach called Fate0 merges the attention features before and after the editing process. Text2 Video 0 directly simulates movements by translating the latent factors, while Pix2 Video links the latent factor of the current frame to that of the previous frame. However, these approaches heavily rely on cross-frame attention and early-stage fusion of latent factors to enhance temporal consistency. As we will illustrate later, these strategies primarily address high-level styles and shapes, and are less effective in maintaining texture and detail consistency across frames. Diverging from these methods, our approach proposes a unique pixel-aware cross-frame fusion of latent factors, which successfully ensures temporal consistency at the pixel level. Section Summary. Several video editing methods have been proposed, including Video Diffusion Model, Imagine Video, Make a Video, Tune a Video, Edit a Video, Video P2P, and Vid2 Vid0. These methods rely on cross-frame attention and early-step latent fusion to improve temporal consistency, but they are less effective in maintaining cross-frame consistency at the level of texture and detail. In contrast, the proposed method achieves pixel-level temporal consistency through a novel pixel-aware cross-frame latent fusion. Section: Stable diffusion. Stable diffusion is a type of model called a latent diffusion model. It operates in the latent, or hidden, space of an autoencoder. For those unfamiliar with this term, an autoencoder is a type of artificial neural network used for learning efficient codings of input data. In this model, we have two main components: the encoder, represented by E, and the decoder, represented by D. Let's take an image, I, as an example. The encoder takes this image and transforms it into a latent feature, or a compressed representation of the image, represented by x_0 feet. Once we have x_0 feet, we can start the forward diffusion process. This process involves iteratively adding noise to the latent feature. We model the noise addition at each time step t, using a normal distribution. The mean of this distribution is a scaled version of the feature from the previous step and the variance of this distribution is scaled by a term related to a hyperparameter, alpha_t. The noise added at each step is a realization from this distribution. Alternatively, we can also sample x_t, the feature at any time step, directly from x_0 feet. This is also done using a normal distribution, but the scaling factors are slightly different. After the forward process, we enter the backward diffusion process. In this phase, we train a model, AU-net in this case, to predict the noise that was added in the forward process and to recover x_0 feet from x_t, the feature after the forward diffusion process. An important aspect to note is that after a sufficiently large number of time steps, x_0 feet gets completely distorted so that x_t becomes a standard Gaussian random variable. In the backward process, the U-net learns to predict valid x_0 feet values from these random Gaussian noises. We can also predict x_t1, the feature at the previous time step, based on x_t, the feature at the current time step, using a deterministic sampling approach. The prediction consists of two components: one component representing the estimated x_0 feet at time t, and the other component pointing in the direction of x_t1. Lastly, during the inference process, we can generate a valid x_0 feet by sampling from standard Gaussian noise using the deterministic sampling approach, and decode x_0 feet to produce the final generated image, I_prime. This is done by using the decoder, D, of our autoencoder. Section summary. The stable diffusion model operates in the latent space of an autoencoder, where a diffusion forward process adds noise to the latent feature of an image, and a U-net is trained to predict the noise of the latent in the diffusion backward process to recover the original image. The model can sample a valid latent feature from a standard Gaussian noise during inference and decode it to generate a new image. Section: ControlNet. We introduce ControlNet, a feature within the stable diffusion process that provides more precise spatial control over the outcome. Its primary function is to accept additional conditions, such as edges, depth, and human poses, effectively enhancing the clarity of the output. ControlNet uses what we call an extra condition, denoted as C_F. When incorporated, this alters the noise prediction of our U-net model, represented by epsilon_theta, x_t, t, c_p, c_f. This means the prediction takes into account not just the current state and time, denoted by x_t and t respectively, but also the additional conditions represented by c_p, our initial condition, and c_f, our extra condition. Unlike instruct pix2 pix, ControlNet can function independently, in parallel, with custom stable diffusion models. It doesn't interfere or depend on these models, instead, it complements them, providing an additional layer of control. In our broader framework, we employ ControlNet to offer structural guidance from the input video, aiming to enhance temporal consistency. This is a crucial step towards constructing a versatile, zero-shot video-to-video, V2V, translation system. Consider a video made up of n frames. Our objective is to transform this video into a new version, using artistic expressions defined by text prompts and/or tailor-made stable diffusion models. This translation process is performed in two parts: keyframe translation and full video translation. During the keyframe translation phase, we incorporate hierarchical cross-frame constraints into our pre-existing diffusion models. This allows us to create coherent keyframes. Subsequently, in the full video translation phase, we use a method that involves time-sensitive matching and blending to disseminate these newly rendered keyframes across the rest of the video frames. Section Summary. The paper introduces ControlNet, a side path to stable diffusion that accepts extra conditions like edges, depth, and human pose to improve spatial controllability. ControlNet is used to provide structure guidance from the input video to improve temporal consistency in a general zero-shot V2V framework. The framework consists of two parts: keyframe translation and full video translation, which use hierarchical cross-frame constraints and temporal-aware matching and blending to render coherent keyframes and propagate them to other frames. Section 4.1 Keyframe Translation. Section 4.1 is dedicated to explaining the process of keyframe translation. A diagram is used to visually represent this process, which is a T-step sampling method for the translation of keyframes. The procedure starts similarly to the SD edit technique. We start with a certain equation, which in layman terms can be explained as follows. The result is derived from the sum of the scaled initial frame, where the scale is the square root of a certain value, which we'll call alpha, related to the step t, and a term involving the step t, a noise variable scaled by 1 minus alpha. The noise variable is drawn from a standard normal distribution. Instead of using pure Gaussian noise, this process employs a noisy version of the input video frame's latent code, which represents its inherent properties. This equation provides users with the flexibility to decide how much detail from the original frame they want to maintain in the final output. They do this by adjusting the parameter t, with smaller t values leading to higher detail preservation. Throughout the sampling of each frame, we use the initial frame as a fixed reference or anchor frame, along with its preceding frame, to ensure that the overall style remains consistent and that there is local temporal consistency between frames. We then apply a technique known as cross-frame attention at every step to ensure this global style consistency. Furthermore, in the early steps of the process, we combine the latent feature, which captures the inherent properties of the frame, with the aligned latent feature from the preceding frame. This helps to establish rough alignments of the overall shape. In the middle steps of the process, we use the latent feature in conjunction with the encoded warped anchor and outputs from the previous stages to establish fine alignments at the texture level. Finally, during the last steps, we make adjustments to the latent feature distribution to ensure color consistency across the frames. To simplify our discussion, we will use the notation I equals O, n, to refer to the keyframes in this section. These are frames that are of significant importance in the video. Section Summary. The T-step sampling pipeline for keyframe translation begins with a noisy latent code of the input video frame, allowing users to adjust how much detail is preserved in the output by adjusting t during sampling. The first frame is used as an anchor frame and its previous frame is used to ensure global style consistency and local temporal consistency. Cross-frame attention is applied for global style consistency, while latent features are fused for rough shape alignments in early steps and encoded warped anchors are used for fine texture alignments in mid-steps. Finally, the latent feature distribution is adjusted for color consistency in late steps. Section 4.1.1 Style-Aware Cross-Frame Attention. We've devised an approach to improve zero-shot video editing, called Style-Aware Cross-Frame Attention. Like other methods, we've modified the UNet structure by swapping self-attention layers with cross-frame attention layers. This modification ensures that the overall style of the edited frame, denoted as I', is regulated to match the style of the initial and the previous frame, represented as I'1 and I'1 respectively. In the original model known as stable diffusion, each self-attention layer takes in a latent feature of the frame, V_I. In simpler terms, these latent features are the underlying properties or characteristics of the frame. This latent feature is then mapped into three separate components: the query, key, and value, represented as Q, K, and V, respectively. We achieve this mapping via linear projections with the help of pre-trained matrices. The output is then calculated by applying the self-attention function, which involves taking the softmax of the dot product of the query and key, scaled by the square root of d, and multiplied by the value. On the other hand, in our cross-frame attention mechanism, we borrow the key and value from other frames, specifically the first and previous frames, to construct the output. This technique aims to identify and incorporate similar patches from other frames into the frame we're currently working with. As a result, the style of the edited frame aligns with the style of the initial and previous frames. Conceptually, we can think of self-attention as finding matching patches within the same frame and combining these patches. In contrast, Cross-frame attention is like identifying matching patches across different frames, and then merging them. Hence, the style of the edited frame inherits that of the initial and the previous frames. Section summary. The paper proposes a style-aware cross-frame attention method to regularize the global style of the output frames in zero-shot video editing. This method replaces self-attention layers with cross-frame attention layers to match the style of the first and previous frames. Cross-frame attention fuses corresponding patches from other frames, while self-attention matches and votes within a single frame. Section 4.1.2 Shape-Aware Cross-Frame Latent Fusion. We're now going to discuss a method we use called Shape-Aware Cross-Frame Latent Fusion. At the moment, cross-frame attention primarily focuses on global style. Our goal, though, is to maintain consistency across frames in terms of both local shape and texture. To achieve this, we apply a technique known as optical flow, which allows us to manipulate and merge latent features. To help you understand this better, let's use some terms. Let's imagine that W_I_J represents the optical flow going from frame I_J to frame I_I, and M_I_J stands for the occlusion mask of the same movement. If we then have X_T_I, that would be the latent feature for a given frame I_I at a specific time step, t. When it comes to updating the predicted features, we have an equation that we can express verbally. The new predicted feature at time step 0 for frame I_I is determined by the product of the occlusion mask and the existing predicted feature. Then we add a component, which is the product of 1 minus the occlusion mask and the warped feature of the reference frame, with warping given by optical flow. We ensure that the resolution of the optical flow and the occlusion mask match the resolution of the latent feature, but we don't delve into the details of this downsampling process in this paper. Next, we've noticed something interesting. When choosing a reference frame, our experiments suggest that an anchor frame, i.e., the first frame, j=0, gives us better guidance than the previous frame, j=I1. Lastly, a word of caution. If we attempt to interpolate elements in the latent space, we may run into some unwanted effects, like blurring and shape distortion, especially at later steps. As a result, we've chosen to limit our fusion technique to early steps to provide rough guidance on shape. Section summary. The cross-frame attention is limited to global style, so optical flow is used to warp and fuse the latent features to ensure cross-frame local shape and texture consistency. The fusion is limited to early steps for rough shape guidance to avoid blurring and shape distortion caused by interpolating elements in the latent space. The anchor frame provides better guidance than the previous frame. Section 4.1.3 Pixel-Aware Cross-Frame Latent Fusion. In this section, we present our approach to maintaining the quality of low-level texture features during the video processing, which we call Pixel-Aware Cross-Frame Latent Fusion. Instead of transforming the latent features directly, we propose a different approach where we warp prior frames and then re-encode them back into the latent space for fusion. However, this approach is not without challenges. The process of encoding and then decoding the frames can introduce distortions and color bias. These issues accumulate over the frame sequence and could lead to distorted results. The distortion can be noticed after performing encoding and decoding 10 times, as shown in Figure B. One way to address this problem is to adjust the decoder's weights to match each image. But, this solution is not efficient for long videos. To efficiently tackle this problem, we propose a new method, Fidelity-oriented zero-shot image encoding. The principle behind our method lies in our observation that the information lost each time in the iterative auto-encoding process is consistent. With this knowledge, we can forecast and compensate for the information loss. Let's put it in simple terms. For any given image I, we perform the process of encoding and decoding twice. The first time, we get the encoded and decoded results x_r_0 and I_r, and the second time we get x_rr_0 and I_rr. We assume that the loss of information between the original state and the first encoding, x_0 to x_r_0, is proportionate to the loss between the first and the second encoding, x_r_0 to x_rr_0. Next, we define a new encoding process E', which compensates for the loss by adding the difference between the first and the second encoding results to the first encoding result. In mathematical terms, this compensation involves adding a multiple, lambda_e, of the difference between x_r_0 and x_rr_0 to x_r_0. We found that a lambda underscore e value of 1 yields good results. However, to avoid potential artifacts introduced by this compensation, we add a mask m underscore e. For example, this mask helps to avoid issues like blue artifacts near the eyes, as shown in figure C. This mask indicates areas where the difference between the original image and the re-encoded image after applying E' is below a certain threshold. Ultimately, our novel fidelity-oriented image encoding process, E*, is represented by the following formula. We add to x_r_0 the result of multiplying m underscore e by lambda underscore e, and the difference between x_r_0 and x_rr_0. As illustrated in figure D, our method is effective in preserving image information even after encoding and decoding the image 10 times. Section summary. The authors propose a fidelity-oriented zero-shot image encoding method to solve the problem of distortions and color bias that accumulate along the frame sequence when encoding and decoding previous frames for fusion. They observe that the amount of information lost in the iterative auto-encoding process is consistent and use this to predict the information loss for compensation. Their novel fidelity-oriented image encoding method preserves image information well even after encoding and decoding multiple times. Section. Structure-guided inpainting. In this section, we discuss a method called structure-guided inpainting, a technique we use to ensure pixel-level consistency in our images. This method essentially involves using information from multiple frames and melding them together in a specific way to create a final composite image. To achieve this, we start with an anchor frame, we'll call it I0, and the frame immediately before the current one. Let's refer to it as E1. We adjust these frames to fit the orientation of the current frame, which we'll call the ITH frame. Now, imagine there's also a roughly rendered version of the ITH frame, which we'll refer to as bar E. Now, we'll blend these frames together. How do we do that? We first merge the warped E1 frame and bar E, giving more weight to the region where the previous frame has less influence. This composite image is then overlaid on the warped anchor frame I0, again ensuring that the areas where the anchor frame has less influence gets more of the composite image. The result is a fused frame. Let's call it ~E, which provides pixel references for the sampling of the ITH frame, E. In simpler terms, we want the ITH frame to closely match this fused frame outside a certain area, and match the structure guided from our network called ControlNet inside that area. This certain area we're talking about is represented by a mask, MI, which is an overlap of the influence regions from the anchor and the previous frames. To represent this concept mathematically, we use an equation that describes how each pixel is assigned a value in this inpainting process. We denote the pixels in the ITH frame by x and the time index by t1. For each pixel, we apply a value from either the fused frame or from the previous state, depending on whether the pixel is inside or outside the mask MI. To summarize, the structure-guided inpainting method allows us to create an image that effectively fills in the gaps, taking into account the context from previous frames as well as the guidance from our ControlNet structure. Section summary. The authors use structure-guided inpainting to ensure pixel-level coherence in their video frame fusion. They overlay anchor frames and previous frames on a rough rendered frame to create a fused frame, which serves as a reference for sampling the current frame. They use structure guidance from ControlNet to inpaint the current frame and ensure coherence. Section 4.1.4 Color-Aware Adaptive Latent Adjustment. In Section 4.1.4, we adjust the characteristics of an intermediate image, denoted as _i_tritero0, using adaptive instance normalization, ADAIN, to align its color statistics to that of a target image, labeled as _1_tritero0. This step helps maintain consistency in the color style throughout all key frames of the video. In Section 4.2, we discuss our approach to full video translation. To manage the translation of frames that contain similar content, existing video frame interpolation algorithms work pretty well. They can propagate key frame details to neighboring frames effectively. Yet, these methods cannot generate new content like diffusion models can. To strike a balance between the quality of output and the efficiency of the process, we selectively apply our adapted diffusion model only to the key frames. To fill in the gaps between these key frames, we utilize a patch-based frame interpolation algorithm. We pick keyframes evenly across the video for every Kate frame, denoted as I_0, I_K, I_2K, and so forth. These keyframes are then processed using our diffusion model to generate corresponding output frames, labeled as I_prime_0, I_prime_k, I_prime_2k, and so on. Let's take the first set of k frames as an example. The frames between I_prime_0 and I_prime_k are filled in through interpolation. We use patch-based propagation to generate intermediate frames from I_prime_0 and I_prime_k, denoted as I_prime_0_1 to I_prime_0_k1 and I_prime_k_1 to I_prime_k_k1, respectively. Finally, we blend these intermediate frames with a technique known as temporal-aware blending to get the final set of frames labeled as I_prime_I. The specifics of this process are detailed later in the paper. Section summary. The authors propose a color-aware adaptive latent adjustment technique to maintain color-style coherence throughout the keyframes in full video translation. They apply their adapted diffusion model to the keyframes and use a patch-based frame interpolation algorithm to render the remaining frames based on the coherent keyframes. This approach balances quality and efficiency while allowing for the creation of new content. Section 4.2.1 Patch-based propagation. In Section 4.2.1, we talk about our method of patch-based propagation. What we're trying to do here is find a way to densely map correspondences between a keyframe and its neighboring frames. We then use this mapping to alter the keyframe coherently. To achieve this, we use a guided path matching algorithm. This algorithm is led by color, position, edge, and time. In Section 4.2.2, we dive into our temporal-aware blending method. Here, the goal is to blend two specific frames, referred to as I'0 and I'(k). We use a special pixel selection mask, M, to do this, and it's based on the error generated from patch matching. To put it more simply, the mask M comes from another mask, called hat_M, which denotes regions where the patch matching error is lower for I'0 than it is for I'(k). This mask, hat_M, equals 1 for a pixel P when the patch match error for I'0 is less than the patch match error for I'(k) at the same pixel. To maintain consistency over time, we start with a mask, M0, that contains only ones. When updating, the previous mask, Mi-1, is modified to a preliminary mask, bar Mi, through a process called optical flow, represented by Wi-1. Only the pixels where hat_M equals 0 are allowed to be updated in bar M to create M. This ensures that a pixel, once it moves onto the next keyframe, does not return to the previous keyframe. The frame that results from this blending process is then used as a reference point for contrast-preserving blending over I'0 and I'(k) to produce the final result. Unlike some methods, we decided not to use a process called Poisson fusion. Our observations led us to believe that this sometimes results in blurry textures and flickering around the keyframe. Section summary. The patch-based propagation method finds correspondences between keyframes and neighboring frames to warp the keyframe. A guided path matching algorithm is used for dense correspondence prediction. The temporal-aware blending technique combines two frames based on a pixel selection mask derived from patch matching error, and preserves temporal consistency by warping the previous mask to an initial one with optical flow. The resulting blended frame serves as a histogram reference for contrast-preserving blending to obtain the final result. Poisson fusion is not used to avoid blurring textures and flickers. Section 5.1 Implementation Details. We carried out our experiments using a single NVIDIA Tesla V100 graphics processing unit, GPU. For the task, we utilized models fine-tuned and optimized with the local response attention, LoRa, method, which is based on Stable Diffusion 1.5. In the context of Stable Diffusion, there is usually a maximum of 1,000 steps, denoted as T_max. However, we customized these steps for our sampling pipeline, setting them in the following manner. We designated the starting point of the sampling, denoted as T_s, as 10% of T_max, the initial point of projection, denoted as T_p0, as 50% of T_max, the final point of projection, denoted as T_p1, as well as the point of attention, denoted as T_a, as 80% of T_max. We fine-tuned the number of steps, T, for each video. We employed ControlNet to impart structure guidance using edges. The weight of control was fine-tuned for each video. For estimating optical flow, we used a method called GM flow. During the complete video translation process, by default, we selected keyframes after every set of 10 frames, denoted as K. The videos we tested were from two separate sources and each video was resized so its shorter side had 512 pixels. In terms of the time taken to run the procedure, for videos of 512 by 512 pixels, the translation of keyframes took about 14.23 seconds per frame, and for non-keyframes, it took approximately 1.49 seconds per frame. Overall, the entire video translation took around 1.49 plus 12.74 divided by K seconds. For each frame. Upon the publication of this paper, we plan to make our code available for public use. Section summary. The experiment was conducted on one NVIDIA Tesla V100 GPU using fine-tuned and LoRa models based on Stable Diffusion 1.5. Stable Diffusion uses T_max equals 1000 steps, and for the sampling pipeline, T_s, T_p0, T_p1, and T_a were set to default values, with T tuned for each video. ControlNet provided structure guidance, and GM flow was used for optical flow estimation. Full video translation took about 14.23 s and 1.49 s per frame for keyframe and non-keyframe translations, respectively, with a total time of 14.23 plus 1.49, K1, K equals 1.49 plus 12.74 per kilosecond per frame. The code will be released upon publication of the paper. Section 5.2 Comparison with State-of-the-Art Methods. In this section, titled, Comparison with State-of-the-Art Methods, we look at 4 recent approaches to zero-shot video translation. These include Vid2 Vid0, Fate0, Pix2 Video, and Text2 Video 0. Focusing on keyframe translation when K equals 5. We discovered that the official programming of Vid2 Vid0, Fate0, and Pix2 Video doesn't support ControlNet, a crucial component for these tasks. When we tried to load custom models into these programs, they weren't successful in producing realistic results. For instance, Vid2 Vid0 generated frames that bore no resemblance to the input. Consequently, we could only apply customized models with ControlNet in Text2 Video 0 and our proposed method. When visualizing the results, it was clear that Fate0 could reproduce the input frame but fell short in adapting it to fit the prompt. Vid2 Vid0 and Pix2 Video, on the other hand, modified the input frame too much, leading to significant shape distortion and inconsistency between frames. While Text2 Video 0 was able to produce high-quality individual frames, there was a lack of continuity in the local textures. In contrast, our method clearly stood out in terms of the quality of the output, how well it matched the content in the prompt, and the temporal consistency. However, since we don't have ground truth data, it's not possible to use conventional metrics like Frechet video distance, FVD, for evaluation. Instead, to quantitatively assess the quality, we conducted a user study with 23 participants. They were asked to pick the best results from the 5 methods, taking into consideration 3 factors. 1. How well the results balance between the prompt and the input frame. 2. The temporal consistency of the results. And 3. The overall quality of the video translation. The average preference rates were calculated across 8 test videos. We found that our method achieved the highest rates in all 3 criteria, demonstrating its superior performance in comparison to the other 4 methods. Section summary. The section compares the proposed method with 4 recent zero-shot methods on keyframe translation with K equals 5. Only Text2 Video 0 and the proposed method use the customized model with ControlNet. The proposed method demonstrates clear superiority in terms of output quality, content and prompt matching, and temporal consistency, as confirmed by a user study with 23 participants. Section. Hierarchical cross-frame consistency constraints. We're exploring a concept we call hierarchical cross-frame consistency constraints, which is a fancy term for ensuring a video remains visually coherent from one frame to the next. This idea is illustrated by comparing results from videos that use these constraints against those that don't. Our method particularly shines when handling videos containing a blend of simple movement in the first part, transitioning to complex 3D rotational movements in the latter half. For the best understanding of this temporal consistency, we recommend watching these videos on our project website. An element of our approach is cross-frame attention, which plays a vital role in maintaining a uniform style throughout the video. For instance, it helps to keep the hair color the same as it was in the first frame. Alternatively, it allows for the hair color to change according to the input frame. It's worth noting that we've made this color adjustment adaptable to give users the freedom to decide the color trajectory. However, these global constraints we've talked about can't track the minute local movements, which is where our shape-aware latent fusion, or SAW fusion, comes into play. This technique works by adjusting the inherent features of elements within a frame, like moving a neck ring, although it struggles with maintaining exact pixel consistency for complex movements. To overcome this limitation, we developed a pixel-aware latent fusion method, or PA fusion, which is adept at rendering the finer aspects such as hairstyles and skin blemishes consistently. Our studies and figures show just how effective this PA fusion can be. Despite our ControlNet's ability to guide overall structure well, it can struggle with maintaining consistency in local textures due to the random changes introduced by noise addition and denoising. These disturbances can lead to missing elements or altered details within the frames. To counter this, our PA fusion technique takes into account pixel information from prior frames to restore and preserve these minute details. Lastly, by maintaining this consistency between keyframes, we're able to effectively lessen the occurrence of ghosting artifacts in frames that are interpolated from these keyframes. This leads to a smoother and more consistent video representation. Section summary. The paper proposes a method for maintaining consistency in global style and local movement in video frames. The approach includes cross-frame attention, adaptive latent adjustment, shape-aware latent fusion, and pixel-aware latent fusion. The proposed pixel-aware latent fusion effectively restores missing elements and altered details by utilizing corresponding pixel information from previous frames, reducing ghosting artifacts in interpolated non-key frames. Section. Fidelity-oriented image encoding. We are here to delve deeper into our method of high-accuracy image encoding, a topic which we discussed in several figures throughout the paper. We've taken two pre-existing models, known as Stable Diffusion's officially released autoencoders, to put our method to the test. These models are the fine-tuned F8FT-MSEVAE and the more loss-prone KLF8VAE. Unfortunately, the fine-tuned model sometimes creates artifacts, while the original model tends to distort color as shown in Figure B. However, we found that our proposed high-accuracy image encoding effectively mitigates these issues. To assess the success of our method quantitatively, we calculated the mean squared error, MSE, which is a measure of the difference between the original image and the one recreated after several rounds of encoding and decoding. This was done using the first 1,000 images of the MS-COCO validation set, as shown in Figure. The results of this test corroborated our visual inspections. It's clear that our method drastically reduces the buildup of errors when compared to traditional encoding techniques. We also applied our encoding method to the process of video translation as shown in Figures B and C. Here, we used only the prior frame without the anchor frame in equation to enhance the visualization of error accumulation. Our method mostly curbs the loss of detail and color bias that lossy encoding can cause. Furthermore, our process incorporates an anchor frame and adaptive latent adjustments, which serve to fine-tune the translation. As shown in Figure D, this results in a process where hardly any errors are visible. Section summary. The authors present a fidelity-oriented image encoding method that effectively reduces artifacts and color bias in autoencoders. They report quantitative evaluation results showing that their proposed method significantly reduces error accumulation compared to raw encoding methods. The authors also validate their encoding method in the video translation process, where it mostly reduces the loss of details and color bias caused by lossy encoding. Section. Flexible structure and color control. The system we're proposing allows for adaptable control over content preservation through the variable x_t. Instead of initializing x_t with Gaussian noise, as shown in Figure B, we use a noisy latent version of the original frame. This enables better detail preservation, as shown in Figure C. You can tweak the value of t to balance the content and the prompt. There may be instances where the input frame introduces unwanted color bias, like a blue sky in a Chinese ink painting. We've provided a solution to this problem, a color correction option. This feature adjusts the input frame to match the color histogram of the frame generated by setting x_t equal to z_t, as depicted in Figure B. When we use the color-corrected frame as input, seen in the bottom row of Figure A, the end result, or rendered image, bottom rows of Figures C, F, is a better match to the color suggested by the prompt. Let's move on to practical applications of our method. Figure presents some examples. With prompts like a cute cat, fox, hamster, rabbit, we can apply text-guided editing to morph a dog into other types of pets, as demonstrated in Figure A. By using tailored modes for producing cartoons or photos, we can realize both non-photorealistic and photorealistic rendering. This is shown in Figure B and Figures C, D, respectively. We also showcase our ability to generate dynamic virtual characters based on novels and manga, taking cues from real human videos and a prompt describing the desired appearance. This is exhibited in Figure. For further examples of what we can achieve with our system, refer to Figure. Section Summary. The proposed pipeline allows for flexible control over content preservation by using a noisy latent version of the input frame to better preserve details. Users can adjust the value of T to balance content and prompt, and a color correction option is provided to adjust the input frame to match the color histogram of the frame generated by X_T equals Z_T. The method can be applied to perform text-guided editing, generate non-photorealistic and photorealistic rendering, and synthesize dynamic virtual characters based on a real human video and a prompt to describe the appearance. Section 5.5 Limitations. Our research does have certain limitations that are important to acknowledge. These are most evident in several typical instances where our approach fails to produce the desired results. Primarily, our approach is heavily dependent on optical flow. So, if the optical flow isn't accurate, our method may result in unintended and undesirable effects. For example, we can only maintain intricate patterns, such as embroidery, if there is a consistent correlation across the frames. If that correlation isn't present, our PA fusion technique doesn't work effectively. Secondly, our technique presumes that the optical flow remains the same both before and after the transition. However, this might not be the case when there are substantial changes in appearance. In such instances, the resultant motion may not be correct. While we can partially solve this problem by setting a smaller T value, doing so might negatively impact the desired styles. Furthermore, discrepancies in the optical flow will correspond to discrepancies in the transition keyframes, potentially leading to double image effects after implementing temporal-aware blending. Additionally, we've noticed that our method struggles to preserve smaller details and minor movements. For example, intricate accessories or subtle eye movements may not be well captured during the transition. Lastly, our technique relies on uniform sampling of keyframes, which might not always be the best approach. Ideally, the keyframes should contain every unique object. If they don't, the propagation process won't be able to generate unseen content. For instance, if a hand doesn't feature in the keyframes, our method will struggle to create it. To overcome this last limitation, one potential workaround could be to allow for user interactive transitions. Here, users would have the ability to manually assign new keyframes based on the results they have seen previously. Section Summary. The limitations of our method are illustrated in the figures, where inaccurate optical flow can lead to artifacts and the proposed PA fusion will have no effect if cross-frame correspondence is not available. Our method assumes the optical flow remains unchanged before and after translation, which may not hold true for significant appearance changes, and small details and subtle motions cannot be well preserved during the translation. Additionally, we uniformly sample the keyframes, which may not be optimal, but user interactive translation can be a potential solution.